Right, let's see how this quantization works with our model of the atom. So what we're taking a look at here is what's known as the Bohr model of the atom. It's not totally accurate, but it's going to work really well for the level that we're trying to achieve. So as we know, an atom in the middle has a nucleus. And then around this atom in this Bohr model, we have orbits, which are where our electrons will reside. Right, so these are orbits. This is where the electron is allowed to be. And just like the quantum realm, the electrons can only be on these orbits. They are now not allowed to be anywhere in between. And so we can say that an electron is right here. And then if we think about it, if we add some energy into this electron, we can excite this electron so we can have it hop up into a higher orbit. And then eventually, just like if you throw a ball up in the air, it comes back down, this electron will come back down. It'll relax back down into this orbit. And whenever it does, it'll release energy in the form of light. And what's weird about the atom is that these energy levels are quantized. So these electron energy levels, which we'll later call orbitals, which we'll later call orbitals, are quantized. Which means that only some, we'll call them heights, are allowed. And if you think about that, it's very different from our kind of classical world. So for example, if you had your hand and then you threw a ball up into the air and then it dropped back down, every time it drops back down, it's going to release some form of energy. And we can throw this ball at whatever heights we want to, right? And all heights in between. But when we get really small, when we get to the level of the atom, that ends up not being true. The ball or the electron can only exist at certain heights. And we see this in our atom emission spectra. So let's take a look at this little diagram that I have right here. So on the top, we have the white light spectrum. So white light is just a combination of all possible lights. And then what we have down here is the hydrogen light spectrum. So what we're doing is we're taking an atom of hydrogen, we're adding some energy, and then it's releasing that energy back out. And that energy corresponds to these frequencies of light. So let's take a look at it. We have our orbitals. I'm going to call them n equals 1, n equals 2, n equals 3, and then n equals 4, right? So you notice that when this hydrogen atom releases this light, it can only release specific wavelengths of light. You don't get the whole white light spectrum. You can't throw this ball at any arbitrary heights. It can only be at certain heights. And these heights correspond to these orbitals, right? So they correspond to an electron going from one orbital to another, right? So maybe this red light is this low energy drop from this n equals 2 to this n equals 1. Maybe this blue one is from n equals 3 down to n equals 1. And then this more kind of purplish one would be an even larger jump, maybe from n equals 4 to n equals 1, right? So what you can see is that these levels are quantized. So you might be asking yourself, why are only some levels allowed? And again, that comes down to some quantum mechanical weirdness. Just like a wave, we thought it was, or just like light, we thought was a wave. Einstein actually said, well, sometimes it acts like matter. Sometimes it acts like a particle. That's the same thing with electrons. We've thought of electrons as particles as having mass and volume, but they actually have some wave-like properties as well. And so this quantization is a manifestation of the wave-like properties of electrons. And so we can make a little analogy to help explain this. We can think about a guitar string, right? So we've got a guitar string, and of course it's attached to two ends of our guitar. So one thing, the guitar or the string could be totally flat. We could pull the guitar string up at one point to make this little kind of loop. We could make it so that we have two kind of peaks, if you will, where one is an upper peak and one is a lower peak. But what you'll notice when you think about a guitar string is we can't have kind of 1.5 peaks. So for example, you can't have it end like this, right? Where we have 1.5 essentially, because these two ends need to be connected to one another. And so this is not possible. And so that's the same thing for our electron if we think about it as a wave. So over here, right, you see this wave. This one is okay because the two ends of the wave connect to one another. If you look over here, these two parts of the wave do not connect with one another. And so this would be associated with an energy level or a state that is not allowed. And that's, again, due to the wave-like properties of an electron. All right, cool. Just one more thing to note. As our energy levels of these orbitals gets bigger, the difference in energy between the levels gets smaller. So let's see what we mean by that. So if we have energy on this side over here, we can put maybe n equals 1 right here, and then maybe n equals 2 right there. So as n gets bigger and bigger, the gap is going to get smaller and smaller. So for example, maybe n equals 3 is right there. You see how the gap between 2 and 3 is smaller than 1 and 2. And that would continue on and so forth, right? N equals 4 would be even smaller gap than the n equals 1, right? You can see how these gaps get smaller and smaller. So a more accurate version of our Bohr model would have our orbitals start off as pretty far from one another, but then get closer and closer to one another. They won't actually be hitting each other. I'm just very bad at drawing a circle. But you get the image. So we'll explore more of this Bohr model as well as a more quantum mechanical model as we go through this series.